I'm Laur Hesse-Fisher, and you're listening to Today I Learned Climate from the Massachusetts Institute of Technology. Imagine for a moment that you're standing on a massive sheet of ice that spans from the high Arctic all the way into the northern United States. At its thickest point, you could drill down through almost 2 miles of solid ice before reaching land. Today on our episode, we are going back in time to visit past versions of our Earth that are wildly different from today's. And why? Well, because the Earth's climate has changed before, many times before, and folks like you have written in and asked us about it. What caused the Earth's climate to change in the past? And what can it tell us about the climate change that we're experiencing today? Fortunately, we know someone at MIT who knows a lot about the history of the Earth's climate.
My name's David McGee, and I'm a professor in the Department of Earth, Atmospheric, and Planetary Sciences at MIT, and I study paleoclimate, which is the study of the natural history of Earth's climate.
It turns out that our planet has changed a lot before we humans came onto the scene. There was a time, for instance, when the whole center of North America was engulfed by an inland sea. A time when alligators crawled in the Arctic and forests flourished near the South Pole. And that's because the Earth has gone through some wild changes in temperature.
Even in the last 1% of Earth history, so the last 45 million years, we've seen changes in the Earth's mean temperature of roughly 30 to 40 degrees Fahrenheit. So huge changes in the mean global temperature.
But how do we know about these big changes in temperature? Well, that really is the story of paleoclimate, and it begins in earnest in the 1700s with some peculiar rocks.
People had noticed boulders that didn't match the local bedrock in places where it didn't really make sense that there should be boulders. In Scotland, in Ireland, around eastern North America, they noticed striations or grooves in the bedrock. And they realized that these striations were things that were observed near modern glaciers. And so people started to piece together this story that there had been very large ice sheets in places where there weren't currently ice sheets.
In 1824, a geologist named Jens S. Mark first proposed that these ice sheets were not just local, but a single, vast mass of ice that once covered much of the Northern Hemisphere. In other words, that the world had undergone an ice age. Over the next century, scientists would find more and more evidence proving his theory, eventually learning that 20,000 years ago, a quarter of the Earth's land surface was covered in ice year-round. And that raised a new question. Just how cold was the Earth during this ice age? To answer that, scientists needed some extraordinary new tools.
Paleoclimate is the art of the possible. There's only so many things that you have that are left over from thousands of years ago. There's even fewer that are left over from millions of years ago, and even fewer from hundreds of millions of years ago. So we have to rely upon natural archives, things that grow or are deposited and somehow record information about the climate around them as they form.
And these archives need to be preserved for a very long time. Scientists have only found a few of these relics of the deep past, often buried in unchanging environments like Antarctic ice or sediments in the deep sea.
And in both of these archives, you have deposits building up year after year after year. And if you're able to drill or core down into them, you essentially have a time machine. I'll just give you an example. There is a certain type of plankton that lives in the surface ocean. These are called foraminifera, and they're about the size of a grain of sand, really small. They happen to form small calcium carbonate shells, so just like a clam might, but they're so small that they're able to float around in the surface ocean.
And when the foraminifera die, Their shells fall to the ocean floor and are preserved in layers of sediment. So what does that have to do with the temperature? Well, it turns out that foraminifera that grow in warmer waters build their shells a little differently.
As the temperature gets hotter, the forams become more sloppy chemists, and they allow more magnesium into their calcium carbonate shell. And so you can measure the magnesium to calcium ratio, and that's a very strong function of temperature.
And there are other time-traveling thermometers found in tree rings, ice cores, and stalagmites deep in caves. When you combine these separate lines of evidence, we can build a window into climates from long ago. And what's more, when scientists tracked these temperature records further and further back in time, a surprising new picture appeared.
They were able to see, oh, wow, it hasn't just been one ice age. There's been this cycle going back and forth between ice ages and warmer periods. So the Earth has been going in and out of ice ages over the last million years at a rate of roughly one cycle per 100,000 years. So you'll have a period like the peak of the last ice age about 20,000 years ago, and then temperatures will rise into warm climates like we've enjoyed for the last 10,000 years.
How? And why? Well, the answer, amazingly, lies not here on Earth, but out in the solar system. So you might know that the Earth orbits the Sun in an ellipsis, not a perfect circle. And the Earth is also tilted. At any time one pole faces the Sun, that's the half of the Earth that experiences summer, and the other half faces away, that's the Earth that experiences winter. But over thousands of years, that orbit and that tilt, well, it shifts.
The Earth's orbit gradually changes as we get pulled by the other planets in the solar system. And so the Earth's orbit becomes more elliptical or more circular through time. The Earth's tilt changes a little bit through time in a cyclical manner.
And gradually, our north and south poles might find that during the summer, they're no longer tilted so strongly toward the sun.
That decreases how much sunlight comes into the Arctic during local summer and makes it harder to melt away the previous winter's snow and ice. And it builds up and builds up and builds up and eventually forms an ice sheet. So then the question is, okay, you're building up some ice sheets in northern Canada and Scandinavia. Why does that make the whole world cold? The real reason that ice ages are a global phenomenon is because as you grow an ice sheet, the ice sheet changes ocean circulation in such a way that more carbon dioxide gets stored in the deep ocean rather than sticking around in the atmosphere.
You probably remember that CO2 is the most important of the heat-trapping gases in our atmosphere that are causing today's climate change. And throughout Earth's history, there's been a close relationship between the average temperature of our planet and the amount of CO2 in our atmosphere. The scientists use the tools of paleoclimate to look at how much CO2 was in the air during the ice ages. In fact, we can actually measure directly the air of the ancient past because some of it is still around.
In Antarctica in particular, as the snow builds up and then gets compressed beneath other layers of snow above it and gradually turns into ice, it traps little bubbles of air. And that air is pristine samples of the ancient atmosphere. And so scientists will collect these ice cores, bring them back to the lab, and then measure directly how much carbon dioxide is in the air from times in the past.
That's really cool. All right, so let's recap. So the Earth shifts slightly in space over thousands of years, making the Arctic summer darker and colder, and ice sheets form and spread, and the ocean's circulation changes. This traps CO2 deep in the ocean. And because there is less heat-trapping CO2 in the atmosphere, the entire planet begins to cool.
And so It's quite a chain of events that leads from the changes in Earth's orbit to the ice ages themselves.
So how much do these changes add up? Well, in the last ice age, which was 20,000 years ago, CO2 in the atmosphere fell by about a third. So do you want to guess how much the Earth cooled as a result?
We now know that in the peak of the last ice age, it was about 10 degrees Fahrenheit colder than it was during pre-industrial times.
Did you guess correctly? Or were you way off? Maybe you're asking yourself now, wait, what? Just 10 degrees? Isn't that the difference between a chilly fall day and a crisp spring afternoon?
Yeah, it's really striking to me how different the world was given only 10 degrees Fahrenheit difference in mean temperatures. So where I'm sitting around Boston, Massachusetts, would have had about a mile of ice on top of me right now.
From just 10 degrees of cooling, which is about 5.5 degrees of Celsius, by the way. But this is the crucial difference between weather and climate. If the weather changes by 10 degrees, well, you put on a jacket. But if the average climate changes by 10 degrees, well, you've got the planet where woolly mammoths roamed as far south as Illinois and Spain.
And then slow changes in Earth's orbit gradually increase how much summer sunlight there is in the Arctic and start to melt back those ice sheets. And the changes go in reverse. So the ocean circulation responds and allows carbon dioxide that has been stored in the deep ocean to come back into the atmosphere.
And those rising CO2 levels warm the entire world, like they are today. Except not quite like today. We really are living through something that's different now. So for one thing, today's climate change is timed all wrong. The Earth's position in space is not setting us up for more warming.
The variations in Earth's orbit are fairly subtle right now, and then they'll get larger over the next few tens of thousands of years. So if there weren't human-caused climate change, we would eventually go back into another ice age.
And a huge difference between the end of the last ice age and today's warming is how fast it's happening now.
So if you look at the warming coming out of the last ice age, temperatures were low until about 17,000 years ago, and then CO2 started to rise and global temperatures started to rise. And they rose that 10 degrees Fahrenheit in about 7,000 years. Modern temperature change is about 10 times faster.
Which means that today we're facing climate change at a speed that even our distant, nomadic ancestors in the Ice Age never confronted, let alone the more recent humans who laid the foundations of civilization as we know it.
The last 10,000 years have been a period of stability in global temperatures. And that period of stability has coincided with the growth of complex human societies and dramatic expansions in human population. And I think it's more than a coincidence.
It is true that the Earth has gone through immense climate change before, many times over, in fact, but human civilization has not, and especially not this fast. Today, we are the ones changing the balance of our atmosphere, and we're the ones who get to decide. Do we want to rapidly shake our planet loose from the stability that we've always known? Or will we be happier and safer if we act to preserve the climate in which humanity has flourished for the last 10,000 years? That is our show for today. Thank you to everyone who sent us in questions about the Ice Ages. You can send us your own question by leaving us a voicemail message at 617-253-3566 or visiting climate.mit.edu/ask. Today, I Learned Climate is the climate change podcast of the Massachusetts Institute of Technology. Aaron Krol is our writer and executive producer. David Lishansky is our sound editor and producer. Michelle Harris is our fact checker. The music is by Blue Dot Sessions, and I'm your host and senior editor, Laur Hesse Fisher. Thank you to Professor David McGee for speaking with us and to all of you for listening. Keep up your climate curiosity.